In this presentation, I am going to explain previous GATE questions and answers for the year 2026, and the topic covered is electrical machines. Now let us see the first question of 2026 GATE question that carries 1 mark. A 15 kVA 1100 volt slash 220 volt single phase 2-winding transformer is configured as a 1.32 kV slash 1.1 kV auto transformer. What will be the rating of the auto transformer? For a 2-winding transformer is converted into an auto transformer, and the 2-winding transformer voltage rating as well as the apparent power rating, that is 15 kVA, that is given. And the question is that what is the rating of the kVA rating of the auto transformer? The options are option A 60 kVA, option B 75 kVA, option C 90 kVA, and option D 100 kVA. With the 2-winding transformer that is shown here, and that is the primary voltage equal to 1100 or 1.1 kV, and the secondary voltage is equal to 220 volt, and the corresponding kVA rating equal to 15 kVA. And based on that, we can calculate what is the primary current, that is 15 kVA is the kVA rating or apparent power rating of the transformer. Therefore, that and voltage is also given, and from that one we can calculate what is the primary current corresponding to 15 kVA 2-winding transformer. The primary current equal to 15,000 divided by 1100, which is equal to 13.63 amperes is the primary current. Similarly, the secondary current is equal to same 15,000 divided by the 220 volt is the secondary voltage, which is equal to 68.183 amperes. Therefore, this current equal to 68.183, and this current is equal to 13.63 amperes. Therefore, this is a 2-winding transformer. This is converted into an auto transformer in this fashion, like that, so that the input voltage rating is now, it is add up, these two voltage are adding, or that is totally it will become, it is equal to 1.32 kilovolt, and the tapping is taken here, and the secondary voltage is equal to, or this auto transformer output voltage is given by, it is equal to 1.1 kV. Therefore, this is auto transformer. This 2-winding transformer is converted into an auto transformer. The question is that what is the rating of this transformer? Now, there are two methods. In one method, we can first, we have the auto transformer. The input voltage is equal to, as we see that one, the total voltage at the input side is equal to 1.1 kV plus 220 voltage, or that is equal to 1320 volt is the total input voltage. And the input current is equal to, actually when it is converted, that is the input current of this corresponding to LV side, which is equal to 68.182 amperes. Therefore, that is the input current and input voltage, and the kVA rating is the product of that one, that will give 90 kVA. Another method is that very simple equation is the relating the kVA rating of the 2-winding transformer and a auto transformer, that is equal to, first we have to find out what is the transformation ratio of the auto transformer. Therefore, the transformation ratio of the auto transformer is equal to 1000 output voltage equal to 1.1 kV or 1100 voltage, and input voltage equal to 1320 voltage. Therefore, we will be calculating what is the transformation ratio of the auto transformer, that is represented as capital K, and that is equal to, we will be getting it is equal to 0.83. Then there's a relation is that the kVA rating of the auto transformer is equal to the kVA rating of the 2-winding transformer divided by 1 minus K, where K is the transformer ratio of the auto transformer. Or substituting that one, we will be getting 15 into 10 raised to 3 divided by 1 minus 0.83, or that's also equal to 90 kVA. Therefore, there are two methods are there. This is the easy method is to remember this equation so that we can calculate what is the kVA rating of the auto transformer once the kVA rating of the 2-winding transformer is given. Therefore, the answer is option C, which is equal to 90 kVA. That's the kVA rating of the auto transformer. Let us see another problem, 2026 GATE question that carries 1 mark. a certain application requires power at a frequency of 16.67 Hz, while the available grid frequency is 50 Hz. A three-phase synchronous motor connected in the 50 Hz three-phase grid driving a synchronous generator is used for this application. Therefore, the synchronous motor is mechanically coupled to another synchronous generator alternator, or that is generating the voltage, the frequency of 16.67, and this frequency is equal to 50 Hz. Which of the following combination is suitable? It is a suitable choice of the number of poles in the motor and the generator. What should be the number of poles of the motor and what should be the number of poles of the generator? Therefore, both are synchronous machine. This is running as a synchronous motor that is mechanically coupled to a alternator or synchronous generator. And the question is that what is the ratio of the poles of the synchronous motor and synchronous generator? And this frequency is equal to 50 Hz and this frequency equal to 16.67 Hz. Now the options are A, pole number 2 and 6, that is motor 2 and generator 6. Next one 6 and 2. Motor is 6 pole and generator is 2 pole. And next one 4 and 6. 4 is the number of poles of the motor and 6 is the number of poles of the generator. And the option D is 6, 4. That is 6 is the number of poles of the motor and 4 is the number of poles of the generator. Now coming to here, since the motor and generator are running the same because they are mechanically coupled, therefore they are running at the same speed, and that is also, since it is a synchronous machine, that will be running at the synchronous speed. And for the synchronous speed you have to calculate. For the synchronous, since it is mechanically coupled, the synchronous speed must be the same, or the synchronous speed of the motor is same as the synchronous speed of the generator because they are mechanically coupled. Therefore, that is n of the synchronous speed of the motor equal to synchronous speed of the generator. Synchronous speed of the motor can be calculated as 120 into corresponding frequency is 50 Hz, 50 divided by the number of poles of the motor. And that should be equal to 120 into the frequency of the generator 16.67 divided by the number of poles of the generator. From this equation we can get it as number of poles of the motor divided by number of poles of the generator equal to 50 divided by 16.67, or that is in the 3 by 1, or the ratio is 3:1 as such. Therefore in this case it is if you see that P of the motor equal to 3 times P of generator, and if for example generator poles are 2, then the motor poles are equal to 3 into 2, which is equal to 6. Therefore the ratio is equal to 3:1. Therefore the answer here corresponding to 2 pole generator, the number of poles of the motor equal to 3 into 2, which is equal to 6. Therefore the answer is option B. Therefore number of poles of the motor, number of poles of the generator equal to 6,2. Therefore the answer is option B. Answer is option B. Now let us see another problem of 2026 GATE question that carries 1 mark. Which of the following option is correct regarding the typical double squirrel cage structure and is used in the induction motor? It is a rotor structure. It is a double squirrel cage. Therefore outer ring is having the large resistance and is having low reactance winding, and here the inner one, it is the high reactance and the low resistance. That is a normal method of connecting. That values of the resistance and inductance for a double squirrel cage induction motor. Now here the options are the option A, at starting a larger portion of the rotor current flows in the outer ring. That is the option A. Option B, at starting the larger portion of the outer current flows in the inner cage. And option C, at rated speed most of the rotor current flows in the outer cage. And option D, the purpose of the double cage structure is to lower the effective rotor resistance at the starting. So these are the 4 options, but for a double squirrel cage induction motor is a specialized AC motor featuring 2 separate parallel rotor winding cages are there. That is, outer has got a high resistance and low reactance, and the inner has got a low resistance and a high reactance. Therefore this at the starting, since the slip is the value is more because near to stationary slip is more. That is, the reactance will be more. Therefore, and of course at a low resistance. And this dual cage portion of high, that since the current is here, the reactance is low, therefore, but compared to this one, here the reactance will be more at the inner cage at the starting. But the starting, the reactance will be less because low value of reactance, X value is low. That is why at the starting, the most of the current will be taken for the outer cage, so that the resistance is high, means that starting torque will be increasing. Therefore, this dual cage design provides a high starting torque and low starting current while maintaining high efficiency and good performance during the normal running condition. That will be running, that is a current will be going through the inner cage in which the resistance will be less and the reactance will be more. But since the slip is small, the reactant, though X value is high, the reactance will be less. Therefore, these are the two cages. Outer cage is having large value of resistance and low value of the inductive reactance, and here large value of inductive reaction, low value of the resistance. Therefore, the answer is at the starting, the larger portion of the rotor current will be flowing to the outer cage of this double squirrel cage structure of the induction motor. Therefore, the answer is option A. At starting, the larger portion of the outer current flows in the outer cage. Let us see another problem of 2026 gate question that carries 1 mark. A 220 bar 12 volt single phase transformer is designed for the use in India and it is rated as 100 VA at 50 Hz. Later, this unit is shipped to the USA where it is used for 110/6 volt. The transformer at 60 Hz. For the voltage rating has been reduced and the frequency is increased from 50 to 60 Hz. Which of the following statement is true? Or that is, to be correct. Option A, no load current drawn would be smaller for operation in the USA compared to that in India. Option B, for the same load current, the losses would be higher in the USA compared to that in India. Option C, the peak magnetic density in the core would be higher while operating in the USA compared to in India. The option D, the eddy current losses in the core would be approximately 44% higher while operating in the USA compared to the India. Therefore, you have to see what is the answer that will be explained in the next slide. Now, continuing the same problem, as we know that in the no load current is the sum of the two components. One be contributing the iron loss, another one is to maintain the magnetic flux. Therefore, the magnetizing current as well as iron loss component of current, the summation of the vectorial sum of this current is the total no load current. Therefore, the no load current equal to the lossy component, normally we call it as working component, and the magnetizing component is represented as IM plus IW. Therefore, the working component that is contributing the losses, that consists of two losses, because of the core loss, that is hysteresis and eddy current loss are the main losses. Under no load condition, hysteresis core loss consists of hysteresis and eddy current loss. And the maximum flux density, that both are proportional to the magnet. One is Bmax square, another one is Bmax to the 1.6. So that depends upon maximum flux density. Therefore, the maximum flux density, we can see that is proportional to the voltage divided by frequency. V/F ratio is that. Therefore, the maximum flux density Bm is proportional to V/F. Therefore, here, as the voltage V reduces, the frequency F also increases. In this case, the voltage rating is reducing. While shifting to the USA, the voltage rating, that level is different. From 220 it is rating to 110. It's primary voltage. Voltage is reducing. At the same time, the frequency increases also. Therefore, V/F, this is increasing and this is reducing. Meaning that V/F ratio reduces or maximum flux density reduces. Therefore, as V reduces and frequency increases, V/F ratio reduces. As V/F ratio reduces, maximum flux density also reduces. And because of reduction in maximum flux density, these losses, hysteresis loss and eddy current losses are reducing. The iron loss, of course, that is, that induce, here reduces, Bm reduces. Iron loss, that is corresponding to that, working component of the current reduces, and no load current I naught also reduces. Because Bmax reduces, these losses will be reducing on the working component that of the current that reduces, or the no load current reduces. Therefore, the no load current drawn would be smaller for the operation in USA compared to the India. Therefore, the answer is option A. Therefore, the corresponding answer is this option A is the answer. Now let us see another problem of 2026 gate question that carries 2 marks. That carries 2 marks as such. 3 single phase 11 kV / 3.3 kV transformers are connected to form 3-phase transformer bank with a connection as shown in figure. That is here A phase, that is normally it is A1, A2, B1, B2, capital C1 and capital C2. This is the primary side, and this is a delta connected one. Therefore, A1, A2 is connected to B1, and B2 is connected to C1, and C2 is connected to A1. Therefore, this is a delta connected primary. And here the secondary side, again that is noted as small a1. Here this is equal to a1, a2, b1, b2, small c1, c2. Here a1 is connected to, small a1 is connected to here b2, or b1 is connected to c2, or c1 is connected to here a2. Therefore, that is the way in which that's also delta connected and the secondary. Therefore, what is the configuration here? Considering the ABC phase sequence here, ABC, the vector group of this transformer is what is the question? Therefore, here options are option A, capital D, small d, 0. That is delta connected primary, secondary also delta connected small d, and the phase shift equal to 0 degree. Or 0 degree means it is the clock, it is 0 position. And here second option DD4, that is as per the primary delta, secondary also delta. 4 means that represent the needle in a clock, 4 o'clock. That much shift is there. That is here shift is that it is equal to 90 plus 30, 120. It is that shift is there. Similarly, here DD6 and option D is DD10. DD10 primary is delta and secondary is also delta, and the phase shift equal to mean that is a 110. 10 means that it is actually the in a clock it is representing the 10 means it is of course the phase shift is equal to 6. Of course that is equal to 60 degree. Therefore that is 60 degree between this one. Primary and secondary, that is a 60 degree. Therefore there are 4 options are there. The question is that what is the connection corresponding to this one? Now let us see in the coming slide. Now continuing the same problem, and here this is the delta connected primary, and this is also delta connected, but the polarity is here A1, A2, here B1, B2, capital C1, C2. For the connection, but here A1 is rather than it is A1 is connected to B2 actually. Here similarly B1 is connected to C2 and C1 is connected to A2. Therefore here if you show the phasor diagram here, this is corresponding to the primary, and here there is this is a secondary representing the phase diagram as such. Or here the phase current, if you see that one here, sorry, for phase voltage, if you calculate the phase voltage of this one, this is represent the phase voltage, this is neutral, virtual neutral, or this is a new phase voltage, phase voltage corresponding the primary side, and the corresponding phase voltage here, that is, you can say this that is represented by this one. Or here it is actually it is a 10th clock position here. Therefore the phase shift here is equal to total 60, or this is leading this one by 60 degree. This one is leading this one by 60 degree. Therefore considering this one, we can see that one, this type of connection, primary and secondary both are delta connected DD, but the phase shift is equal to corresponding to the 10th position in the clock. Therefore it is equal to 10. Therefore the answer is D, DD 10. Therefore answer is option D. Now let us see another problem of 2026 gate question that carries 2 marks. A balanced 3-phase supply is given to a 30 kW 4-pole 400 volts 50 Hz wound rotor induction motor, slip ring induction motor with star connected stator and rotor windings. The motor is driving a constant load torque. Load torque is constant. With shorter slip ring, the machine runs at 1176 RPM. When an external resistance is added, non-inductive resistance is added, or 0.27 ohm per phase is added, it's connected in series with the rotor circuit, the steady state speed is now reduced from 1476 to 1404 RPM. Neglecting the rotation losses, the actual per phase rotor winding resistance, what is the rotor resistance per phase? That is in ohms. That's to be round off to the 2 decimal place. Now coming to this problem here, as you know that 4-pole machine and the frequency is equal to 50 Hz, then the synchronous speed of the motor is given by ns equal to 120 F by P. 120 into 50 divided by 4, or 1500 is the RPM of the induction motor. It is a slip ring induction motor. It is a wound rotor or it's a slip ring induction motor. And with shorter slip ring, that is no external resistance, the slip ring is shorted. The corresponding speed is equal to 1176. That is represented as N1. And the corresponding slip can be calculated, which is equal to Ns minus N1 divided by Ns. Of course, percentage into 100 you have to calculate. Or it is equal to 1500 minus 1476 divided by 1500. It is equal to 0.016. Therefore, the slip corresponding to the shorter condition of this one, that is shorter condition of the slip ring, that is corresponding to N1, that is 1476 RPM. The corresponding slip is equal to 0.016. That is indicated as slip S1. Now, when an external resistance of 0.27 ohm per phase is added, now the speed is reducing from 1476 to 1404. Now corresponding to this speed, what is the slip? That is indicated as S2, which is equal to Ns minus N2 divided by Ns. N2 is given by 1404, that is N2, and that is corresponding slip equal to 1500 minus 1404 divided by 1500, which is equal to 0.064. Therefore, as the rotor external resistance is added series to the rotor winding, or 0.27 ohms, the speed is changing from 1476 to 1404, and the slip is, you can see that when the slip was that is increasing to 0.064. It was 0.016. Now the question is that what is the resistance of the rotor winding per phase? That will be seeing in the next slide. Now continuing the same problem, 2026 gate question, and as we know the basic equation relating the torque and the rotor resistance, reactance, etc. This is the basic relation. Torque is proportional to SR2 divided by R2 square plus SX2 whole square. This relation is the relation relating the torque and the slip and the rotor resistance and the rotor reactance X2. Therefore, that is given this one. And for low slip condition, that is near to the synchronous speed, if the motor is running near to the synchronous speed, low value of the slip, this will be very less compared to this one. Therefore, we can approximate in that case, torque is proportional to, of course, this is cancelling, S by R2. Torque is proportional to S by R2 near to the synchronous speed. Therefore, at normal running condition, that will be near to the synchronous speed. This value will be very less compared to R2, and the torque can be approximately, or that can be written as proportional to S by R2. So that will be using this relation. Therefore, for the constant, since the torque is constant, and the problem it is given that both condition the torque is constant. Since the torque is constant, this relation can be written as the slip, or the slip is proportional to, or since the torque is constant, the slip can be made proportional to the rotor resistance. Now coming to the problem, as we have seen the the rotor slip as corresponding to two cases, that is S2 by S1, because from this equation you can write it as S2 by S1 equal to, or the S2 means the slip corresponding to the motor after adding the external resistance. Therefore, S2 and S1 is the slip corresponding to the shorter of the slip ring condition. Therefore, S2 by S1 equal to the rotor resistance. Our rotor resistance is stands like the resistance of the rotor winding plus external resistance divided by S1 means that is proportional. This is equal to the rotor resistance of the winding. So from this equation, we can substitute S2 by S1 equal to R2 winding plus R external divided by R2 winding. Or here, since we know that S1 equal to 0.016, already we calculated. Similarly, the second case, when a rotor external resistance is added, the slip is increasing or the speed is reducing, the slip is changing to 0.064 and the external resistance per phase equal to 0.27 ohms. Now, we can calculate substituting in this equation 0.064 divided by 0.016 equal to the resistance of the rotor winding plus external resistance added per phase equal to 0.27 ohms divided by the resistance of the rotor winding. Therefore, from this equation, the only unknown is the rotor resistance of the winding per phase, which is equal to 0.09 ohms. Therefore, the answer is 0.09 ohm. Per phase rotor resistance is equal to 0.09 ohms.